I'm Daniel Hayes, and I want to welcome you to the 5eroRISC Senior Design Project, where a new open-source instruction set architecture is coupled with a memory-safe programming language in order to add security to embedded systems such as IoT devices. Project specifications are used to describe the project's functionality. The project must use a RISC-V core with user privilege mode and physical memory protection implemented. The physical memory protection, or PMP, is used to sandbox the user-level programming to protect the rest of the system. All programming must be written in the Rust programming language to incorporate its memory safety guarantees. A machine privilege level trap function will handle any unauthorized operations or system calls. The integrity of device firmware is maintained using a secure bootloader. Lastly, the security protocols should not impact device performance by 5%. The project has one requirement stating that all software developments must be documented with the Git version control system, and it is hosted at the GitHub link provided. I chose the RISC-V instruction set architecture because it has the potential to do what Linux has done for software, but for hardware. With no licensing or royalties, the limits are endless. With support for 128-bit architectures, atomic and compressed instruction extensions, RISC-V is future-proof and can be applied to high-performance computing or constrained embedded devices. The hardware used for project development is a Hi-5 Rev-B microcontroller that features a 320 MHz clock, 8 PMP registers, multiple privilege levels, and a built-in ESP32 wireless chip. An external temperature sensor is connected via I2C. On the software side, Rust Systems Programming Language offers memory safety guarantees through default immutability and strict ownership rules. Rust is not as mature as C yet, but its traits feature, performance, and fantastic community support makes it a great language for embedded systems. In fact, Rust is my favorite language that I have ever used. The project software is written in Rust with some inline assembly. Any blocks of code that is unsafe, for example dealing with raw pointers, are explicitly labeled and contained in unsafe blocks. The hardware boots directly into machine mode where the user mode security is configured before entry. User exceptions and system calls are trapped and diverted to a handler function operating in machine mode. The security protocols handle stack overflows and underflows and prevents the use of unknown system calls. Also, PMP configurations cannot be changed while in user mode, nor can any machine level register be accessed. A simple real-world application reads the temperature and prints it to a terminal over UART. The figure on the right shows how the user mode programming is isolated in the system architecture. Several benchmarking tests were performed at 1,000 iterations per test. It was shown that physical memory protection adds zero overhead as it is enforced by the hardware in parallel. A system call adds 194 cycles of overhead versus a program running in machine mode. The temperature reading program operating in user mode only suffered 0.03% of performance loss, well within the 5% limit. The figure in the bottom left corner shows how system control shifts from user mode to machine mode during a system call. The memory stack figure illustrates how PMP isolates and protects the user-level programming. This project will continue in some aspect for my master's thesis. A secure bootloader was not able to be implemented on schedule, but it is still on the roadmap. New RISC-V hardware continues to be introduced to the market, like the ESP32-C3, which has many security features like an onboard crypto accelerator. Adding an RTOS is also in plan. I'm Daniel Hayes, and I approve this message.